Let us now consider one more example. In this example, let us see if life cycle costing will help us in performing a break-even analysis. Consider this situation. I have a community, and at some distance there is a stream which can generate some amount of power. Let us say we have a microhydel plant, and this microhydel plant can transmit power through lines and reach the community to power the community's electrical requirement. Now let us say the distance between this microhydel plant and the community is d kilometers. Now the other option is, within the community we could have set up a PV system. So one possibility to have a microhydel plant transmit power to the community, and other possibility to have a local PV system to take care of the community's electrical requirements. Now there is an LCC, the hydro system, and then there is an LCC of this PV system. Which one to select is the question. So the LCC analysis will give an economic analysis, and we could also perform break-even, so that we can say what is the break-even point beyond a particular kilometers. I should go for PV system. Less than this particular kilometer, I should go for microhydel system. So this kind of decision can be made from the help of this life cycle cost analysis. So let us see in this example how we can benefit from LCC in this respect. So let me now put on the data for the microhydel plant and the PV plant side by side. For the microhydel plant, let us say the power is 1 kilowatt. The plant installation is rupees 16,000. Cost of transmission and distribution is rupees 18,500. Again, these are conceived values. One will have to do a market survey and obtain realistic values. Cost of the line is 4,000 rupees per kilometer run. And again, I want to stress that the importance here is in trying to follow the process of this LCC to determine break-even. These exact values you can always determine from the market forces. The transmission efficiency is around 30%. And for the PV, the following data is available. So the PV plus balance of system cost is rupees 100 per peak watt. The HAT minimum at that place is 5 kilowatt hours per meter square per day. This means that if you take standard insulation of 1 kilowatt per meter square, for 5 hours you will get this insulation available to give you the same amount of energy, incident energy. Now the life term for both we will consider 25 years, and for both we will take interest rate of 12% per year. Now let us perform this LCC, which is K plus replacement plus maintenance. Now here let us consider only the capital cost. Again, just for understanding the process of this break-even analysis, there will definitely be replacements in both the systems, and there will definitely be maintenance cost in both the systems. But for the purpose of this analysis, because we have seen in previous examples how to go about calculating for replacement and maintenance, I would like to focus more on how to find the break-even points. Therefore, for the purpose of this example, I will take R is equal to 0 and M is equal to 0 for both the systems without loss of generality. So let us just think about the capital cost for now and see how to do break-even analysis. Now for both the systems, hydro and PV, let us find what is the capital cost. Now the capital cost is the installation cost plus the transmission and distribution cost plus the line cost. So we saw that it is 16,000 rupees for installation, 18,500 rupees for transmission distribution, 14,000 per kilometer. So into D is the distance between the hydroelectric plant, the micro-hydel plant, and the community. So we land up with 34,500 plus 4,000 D. Now in the case of the PV cost into the power rating of the PV. So let us say the PV cost is given as 100 rupees per peak watt into X peak watts. Now let us say the power rating of the PV is X. You will see that the X will cancel out for our break even. So it could be any PV rating for now. Probably it could be 1 kilowatt rating. So these two are the capital costs. The capital cost will depend upon how much power you want to decide for the PV array. Now we are taking R is equal to 0, M is equal to 0, R is equal to 0 and M is equal to 0 in both the cases. And now we will calculate LCC. LCC for hydroelectric plant, micro-hydel, is 34,500 plus 4,000 D, and LCC for the PV is 100 into X. X is in watts. The present worth is given by 1 by I, 1 minus 1 plus I to the power of 25. Now remember that we are again taking inflation as 0. One can as well take the inflation values from market forces and apply the formula which contains inflation. So you can find the present worth. We have discussed that. So this is 7.84 for the interest rate given, and this is same for both the systems. So this is the present worth factor, same for both the systems. Next, let us find ALCC for hydro, which is LCC hydro by present worth, which is 34,500 plus 4,000 D divided by 7.84, which will be 4,400 plus 510 D. So this is the ALCC annual LCC life cycle cost for the micro-hydro system, and ALCC for PV is LCC PV divided by present worth, which is 100x divided by 7.84. So this is 12.76x. So this is the ALCC for the PV system. So next, let us estimate the energy generated annually. Now for the hydro, we know it's a 1 kilowatt system into 24 hours because it is capable of delivering 1 kilowatt in 24 hours. It's a hydel system, into 365 days, into transmission efficiency of 0.3. So we will get the energy that is actually usable generated is 2628 kilowatt hours. Now for the PV plant, EPV, we know X watt is the rating. So X by 1000 kilowatt into HAT minimum hours of operation into 365 days will give you into 5 into 365, which is 1.825 X. X being the rating in wattage. So this will be the energy generated by PV. Now let us look at the cost per kilowatt hour. The cost per kilowatt hour is also called unit. So cost per unit. So for hydro, rupees per unit or rupees per kilowatt hour is ALCC hydro by energy generated annually by the hydro. So both are annual terms, 4400 plus 510D divided by 2628. So you'll get 1.67 plus 0.19D. This is a linear equation. So it will be a straight line when you draw a graph of the unit cost versus D. Now for the PV, rupees per kilowatt hour or rupees per unit is ALCC PV by energy generated by the PV, which is 12.76x by 1.825x. X will cancel off, and the rupees per kilowatt is 7 rupees. So this is the cost per kilowatt hour. Now the important thing, let us see how to find the break-even point. So you equate, this cost should be equal to this cost. So let us equate and find out what is the value of D. So that is 28 kilometers approximately. So this 28 kilometers is the break-even point. If the distance of the community from the microhydel station is less than 28 kilometers, you will see that the microhydel plant is beneficial. If the distance of the community from the microhydel plant is greater than 28 kilometers, then you will see that the PV plant is beneficial. So that is basically the takeaway from this break-even analysis. And if the distance greater than 28 kilometers, a local PV plant would be more economical. So this is how you could use LCC even for doing break-even point analysis. I have here with me a script file ex03.m. This is actually the script for solving the third LCC example, and here we just now discussed how to find the break-even point when you want to decide between two systems, which one would be the better one for application and under what conditions. So this is the statement of the problem. Estimate the unit cost of power for microhydel system as a function of transmission distance. Also estimate the unit cost of power of a comparable PV based system as a function of the PV wattage. Find out the break even between these two systems. Now we have worked it out manually. Now this script file will also do the same job, but you can change all these specifications and then try to find out the break-even points for different conditions and different specifications. I will include this, I'll share this file also with you in the resources section. What I have done here basically is to classify it into the following. First, I have the subsystem data of the hydel and subsystem system specifications of the hydel system. So this is for the hydel. Then I have the subsystem data and the system specification of the PV. So I have marked here in brackets PV. So the hydel cost, transmission cost, distribution cost, line cost, all these things I have put together in the system data. And system specifications like the power rating, 1000 watts, transmission efficiency, AMC for the hydro, I kept it as 0. You could include later on to find out what happens with the annual maintenance charges. D, I have kept it at 0. We will just see what happens. X, the rating of the PV system at 1000, and HAT minimum 5. AMC for PV also kept it 0. Then there are common specs like the LCC life term is for 25 years and interest of 12%. Then you do the LCC costing. First, for the hydro system, calculate K or M this fashion. Of course, M and R will turn out to be 0 because we have taken them as 0. Find out LCC, find out ALCC, then the annual energy just like we calculated. This will give in watt hours, and the unit energy cost is ALCC by annual energy, rupees per watt hour. You can convert it to kilowatt hour as I have displayed here by dividing by 1000, multiplying by 1000. Then the display section does the display of all the parameters. Then you do the same exercise for the PV system, calculate the capital, replacement cost, maintenance cost, then the LCC, ALCC for the PV, annual energy generation capability, and the unit energy cost, and then display them. So this is what actually the script file contains. It automates the process of calculation. Therefore, you can quickly change the specification and find out for your systems. Now let us execute this and then see. EX03. When you execute, you will see the display. First you have the LCC calculation for hydro, and the second part contains the LCC calculation for PV. Now see here the unit cost, rupees per kilowatt, or 6.9 or 7 rupees in the case of the PV we calculated, and in the case of the hydro, it's a function of D. 1.67 was when D is 0. So it is 1.67 plus 0.19 D. So D is 0, it is now only 1.67. Now let us say D, I change it to 50. It is greater than 28 kilometers, 50 kilometers. Therefore, hydro will become more expensive. So if I rerun this, so you will see that hydro is 11 rupees, 11.38 rupees more as compared to the PV. PV is more economical. So if you are around that 28 point, both should be of similar values. You can rerun them. So you see it's 7 rupees, is also 7 rupees, both. So break even comes around that point. In this way you can try to use this for solving break even problems.